In this lecture, I'm going to talk about asymptotic fields near the crack tip. And what do we mean by asymptotic fields? We have derived the expression for stresses, in particular stresses on the crack plane. Sigma y, for example, is calculated on the crack plane. That's the crack plane, y equals 0. Westergaard function is defined in terms of complex plane that's based on this xy plane. Full field expression for stress sigma yy is known, but in fracture mechanics, we are especially interested in stress field near the crack tip, because we have shown that the stress sigma y approaches infinity near crack tip. In order to examine this behavior in more detail, we will derive asymptotic representations of stresses as r goes to 0. We place a local polar coordinate system at the crack tip x equals a. And we will derive stresses as r goes to 0. R is not exactly 0. It goes to 0, and those are called asymptotic fields near the crack tip, and they'll provide us with certain information regarding parameters associated with fracture mechanics or brittle fracture behavior. How can we derive the asymptotic stresses? That's an important question, and you are asked such questions in the homework assignment as well. This is the expression of stress for sigma y. Sigma y is real z plus y times imaginary z prime for a mode 1 problem. And for a crack under biaxial loading, z and z prime are given. They are rewritten here. Z is sigma z over square root of z squared minus a squared. And z prime is minus sigma a squared over z squared minus a squared to 3 over 2. Well, this is derivative of z, or their derivative. Now, we can make use of these to find asymptotic representations. Now, z, our variable z here, is in this plane, in the physical plane, corresponds to a point in the physical plane, and z is a plus r times e to I theta, representation of this complex number. Or you will need z plus a and z minus a here. Z plus a is therefore 2a plus r times e to I theta, but r goes to 0. In asymptotic representations, which means that r is much less than a. Therefore, in asymptotic analysis, this is 2a plus r times e to I theta is replaced by 2a. And z minus a from this equation follows that this is equal to times e to I theta. Therefore, for small r, and z squared minus a squared is 2a times r e to I theta. This is z squared times a squared. And square root of this is square root of 2ar times e to I theta over 2. That's the general presentation for the square root. Now I can use this information to write down z and z prime. Westergaard function z is, for example, sigma z over square root of z squared minus a squared, sigma times z, which is a plus r e to I theta, over square root of a squared minus a squared, and this is square root of 2ar times e to I theta over 2. Expand this z, and you will get sigma a over square root of 2ar times e to minus I theta over 2, plus the second term, sigma times square root of r, because r in the numerator is cancelled out by r in the denominator, square root of 2a times e to theta over 2. This is z. But the second term, what can you say about this term? Any suggestions about the second term? Or z? In asymptotic analysis, r goes to 0, and we have square root of r here, and we are going to therefore neglect this term. It will not contribute if r is sufficiently small, if it goes to 0. For this reason, z is equal to the first term. And we introduce here a factor, square root of pi. The numerator and denominator, they are both multiplied by square root of pi, because this is standard notation in fracture mechanics. And the first term becomes sigma times square root of pi a over square root of 2 pi r. A's in the numerator and denominator are cancelled out. And this is the final form for z, asymptotic analysis. Sigma times square root of pi a over square root of 2 pi r e to minus theta over 2. And apply a similar procedure for z prime, second term. Place this. We get minus sigma a squared over z squared minus a squared to 3 over 2. That becomes minus sigma a squared over 2ar to 3 over 2 e2 minus 3I theta over 2. It's using this term, actually. And we can expand this as well. Z is therefore sigma minus sigma a squared over 2ar to 3 over 2 cosine 3 theta over 2 plus second term. And this is the expanded form for z, because e2 minus I theta over 2 is cosine theta over 2 minus I times sine theta over 2. Z is also expanded. These are therefore main results for z and z prime in terms of the polar coordinate r, and its polar coordinates are on theta. We know the expression of sigma y for this problem, not this one. For mode 1 problems, or for this particular mode 1 problem, sigma y is real z plus y times imaginary z prime, and use the final forms in this expression. Sigma y was real z plus y times imaginary z prime This is real Z. Cosine square root of pi a over square root of 2 pi r cosine theta over 2. And this is imaginary Z prime. Substitute them into sigma y. And get this. A real final real expression, but still it can be simplified further. And this is y. Y is replaced by r sine theta. And sine theta is replaced by 2 sine theta over 2 cosine theta over 2. And this r is cancelled out with this r, so square root of r remains here. A squared is cancelled out with a, square root of a. This is reduced by a, square root of a. Multiply both the numerator and the denominator by square root of pi, because that's the standard notation. Somewhat simpler expression for sigma y1. Asymptotic result, or factor out cosine theta over 2, and you'll find the final result. Sigma yy at the crack tip of this problem. Sigma times square root of pi a over square root of 2 pi r times cosine theta over 2 times 1 plus sine theta over 2 sine 3 theta over 2. That's an important expression in fractal mechanics. It gives the stress distribution around the crack. And you can notice certain features. In the denominator, we have square root of 2 pi r as a singularity again. As r goes to 0, this gets out of bounds. This is known as square root singularity in fractal mechanics. Square root of 2 pi r known as square root of singularity. Another function here, we have separate functions of r and theta, another function of theta. This gives the angular distribution of stresses. And a constant term multiplying factor sigma times square root of pi times a. This is the most important result, and we'll talk about this, and we will define this as stress intensity factor. It depends on external stress sigma and half crack length A. The magnitude of this is named as stress intensity factor, and we will see how it's in general defined. Therefore, you have a solution in the local coordinate system here. Theta, and it is sigma y in that coordinate system. Any questions about this finding? I can repeat this procedure to find these asymptotic representations for the other two stress components. Sigma x, sigma xx, and sigma xy at the crack tip. These can also be derived. Actually, you are asked to derive this in the first problem in the homework. The forms are similar. We have square root singularity here, a different function of theta, and stress intensity factor appear in this, or this constant appear as a factor as sigma x as well. Same characteristics of sigma xy. Different function of theta, the square root singularity here, and the constant term, which we will later name as the stress tensor factor. These are therefore the asymptotic fields near the crack tip. Now, I'm going to talk about stress intensity factor. We will actually define stress intensity factor. This is the main parameter in linear elastic fracture mechanics and fatigue applications. Stress intensity factor can be defined for each mode of loading. But that's going to depend on the mode of loading. If there is a mode 1 problem, you can define a mode 1 stress intensity factor. That's going to be shown as K sub 1. Of course, for mode 2 and mode 3 problems, we are going to respectively define K2 and K3, mode 2 and mode 3 stress intensity factors, or you might have a mixed mode problem where all these stress intensity factors exist. And right now, we will consider the stress intensity factor for mode 1 problem. Stress intensity factor is related to asymptotic distributions. It's at the same time related to the full fields. Suppose that this is a crack in a material under an arbitrary kind of loading. There are two crack tips, and stress intensity factor at the crack tip A, this crack tip can be defined. We are looking into the behavior of stress at x equals A. We will remove the square root singularity in the definition. Its K1 is limit R goes to 0. Square root of 2 pi R times sigma y by R comma 0. Now this product allows removal of the square root singularity, and the remaining constant is, as R goes to 0, is defined as the stress intensity factor. Therefore, this is a limit, right? As a limit as R goes to 0. You cannot calculate stress at R equals 0, and for this reason, it is defined as a limit. And stress is multiplied by square root of 2 pi R. Singularity is eliminated. And since this is defined as a limit, as R goes to 0, you can use the asymptotic distribution to find stress intensity factor, K1. It depends on stress, opening mode stress, sigma y, on the crack plane, near the crack. In terms of the polar coordinates. And I can define it in terms of the Cartesian coordinates. Cartesian coordinates are x and y here. And in terms of the Cartesian coordinates, same stress intensity factor, K1 at A, is limit x goes to A plus. We are approaching in this direction from the material side to the crack. Square root of 2 pi x minus A. Now R here is x minus A. times sigma yy x comma 0. Again, stress on the crack plane. And this is going to give you exactly the same result as the definition of the stress intensity factor in terms of the Cartesian coordinates. And I can apply this definition for the other crack tip as well. If the loading is not symmetric, we have different stress intensity factors at these crack tips, x equals a and minus a. And at x equals minus a, the definition is limit x goes to minus a minus. We are approaching the crack from the material side, from left. Square root of 2 pi minus x minus a, because this distance is minus x minus a. It's positive quantity, although everything has minus sign. Minus x minus a is positive, times sigma y x comma 0 is sigma y on the crack plane. Therefore, stress intensity factor gives the strength of the singularity. It's equivalent to strength of the singularity at the crack tip. It has a unique unit, different kind of unit. It is stress times square root of distance, which is megapascals times square root of meters. Unit of stress intensity factor. These are the basic definitions, and they can be applied to calculate stress intensity factor for any problem. There's an example here. What's the stress intensity factor for the problem we have considered up until this point? In other words, what's the stress intensity factor for this crack, which is under biaxial loading at infinity, sigma, x direction, sigma in y direction. You can apply either the asymptotic distribution or the full field distribution to calculate stress intensity factor. First of all, because of symmetry about y-axis, stress intensity factor at A is equivalent to stress intensity factor at minus A. It suffices, therefore, to evaluate stress intensity factor, for example, only x equals A. And how can we do that? We are going to use the main definition. First, polar definition. A1A equals limit r goes to 0 square root of 2 pi r sigma y r comma 0. And since definition is polar, I'm going to here substitute the asymptotic form. What is sigma y r comma 0? If you recall the asymptotic form, and if you substitute 0 for theta, you will get this expression. Sigma y r comma 0 equals sigma square root of pi a or square root of 2 pi r. Left, the right side becomes 1. And multiply this by square root of 2 pi r and evaluate the limit as r goes to 0. These are then canceled out. This is simply a constant, therefore its limit is square root of sigma times square root of 2 pi a. This is therefore the stress intensity factor for this problem. Stress intensity factor is stress times square root of half crack length. Depends on the length of the crack and applied stress. This was a straightforward application of this main definition in terms of the polar coordinates. But I could have used the definition in terms of the Cartesian coordinates. I selected this character at x equals a plus. Therefore, our main definition is k1a equals limit x goes to a plus square root of 2 pi x minus a sigma y by x comma 0. I know the full field expression. Last week, we have derived stress on the crack plane. It is sigma x over square root of x squared minus a squared. Now, you have to substitute this into stress intensity factor and carry out a simplification. You have square root of 2 pi times x minus a here. And when this is canceled out, this in the denominator, and substitute a for x in the remaining terms. Because of limit, these are canceled out. Square root of 2 pi sigma a over 2a. Again, this is simplified to end up with the same expression. K1 equals sigma times square root of pi a. I can directly tell the unit it's megapascal times square root of meters. And we can use any stress unit and any length unit, but standard way of writing this unit in the SI system is megapascal times square root of meters. That was an illustration of the application of the stress intensity factor. I'm going to talk about this in further detail, but right now we have a definition for the stress intensity factor, and we have managed to calculate the stress intensity factor for this problem. And this has applications in brittle fracture. Brittle fracture of this particular material under this loading is examined by using this particular parameter, and we will see how that's possible. And in the next lecture, I'll be talking about the general asymptotic fields for different modes of loading.